Hey, hello, and welcome to my video presentation of the work on complementing an undergraduate software engineering course with formal methods. I assume that everybody has an imagination of undergraduate introduction to software engineering, so I've structured the presentation as follows. The term formal methods does not have a universally agreed on meaning, so we begin with a working definition. Then we discuss a view on formal methods in the context of software engineering that hinges on learning objectives for formal methods in software engineering. And we outline why we see a need for work here. We continue to point out the challenge of teaching towards these learning objectives and present a proposal of a course design, including a particular didactical approach. And finally, we conclude. So, the definition that we adopt here has been phrased by Bernd Westphal and says a method is called formal method if and only if its techniques and tools can be explained in mathematics. This is a rather broad definition, so a lot of software description languages can be in, like requirements patterns, decision tables, sequence diagrams, class and object diagrams, state machines, pre and post conditions, and much more. Now, what is the benefit of having a formal semantics for such software description languages? Well, we can, for example, get automatic consistency analysis for requirements. We can get automatic test generation. We can describe precise acceptance test instructions. We can have unambiguous documentations. We can use exhaustive model checking to check design ideas. And we can apply automatic static analysis to code. Interestingly, a recent survey by Klünder and others published at SEIP 2019 has found that today only a minority of 243 out of 604 responses who know the practice formal specifications stated that they are never used. So only 240 of about 600 say formal methods are never used. This is today the minority. And next to that, we observe a growing interest and use of formal methods in the industry in the broad sense. Not necessarily all at once, yet for each one there is interest and use. So we saw a need to have this observation reflected in our teaching to prepare today's students for a working environment of tomorrow. Where's the problem? Well, we want to introduce formal methods in the context of software engineering, so we need to consider, of course, the software engineers, client customers, the relation to the products under construction, and the relation to today's mostly informal practice of software engineering. Let's zoom in a bit and distinguish a formal method consisting of a description language with syntax and semantics, properties like consistency for requirements, and then analysis algorithms and tools that can check such properties on a given description in a particular formalism. Now, what are the relations that we need to cover in teaching? Well, the engineers need to be able to create models, so they need to know the syntax and semantics of their formalism well in order to formalize understandings of, for example, a design idea. The engineers need to be able to validate formalizations with clients or customers. For example, is the formal description a valid model of a given requirement? Then our software engineers need to be able to operate these algorithms and tools to analyze models. And most importantly, the outcomes of such analysis need to be interpreted with respect to the product under construction, and the engineers need to know what are appropriate actions to be taken. And finally, as I said, we want to discuss formal methods in the context of today's mostly informal software engineering. Now, where's the problem? Why is there work to do? Well, if we look into the popular textbooks such as Ludwig here, or Somerville, or Balzert, or many more, we observe something that I would like to call an extrapolative approach. So they discuss many software description languages on this formality scale ranging from truly informal work in requirements engineering to some semi-formal introduction of modeling diagrams. Then the books may give some motivation why it would be useful to have a formal semantics and tools working on these diagrams, yet they never really go there. So they do not give at least one example of a formal semantics function. Meaning, how do these formal variants of the software description languages look like? This is left to the imagination of the students. They need to extrapolate. What we are after and what we propose is to cover the very same things to connect to today's software engineering and then jump to the right extreme end of the scale and comprehensively introduce a collection of formal software description languages with a selection of formalisms that range between more simple ones, more complex ones, and are applied in the major activities of software engineering. So at least one example for requirements engineering, at least one for structural and behavioral modeling, and at least one for code quality assurance. Here's another challenge. What we have in the middle is a schematic of our one semester undergraduate introduction to software engineering. We have topic areas software process management, requirements engineering, we have architecture and design, we have code quality assurance, and we can imagine that time is already pretty tight. So where do we put this additional material? Well, there's the following observation that if we follow the textbooks named before, we already have a lot of software description languages in there, like process models, like use cases and scenarios, like diagrams for structural and behavioral software modeling, like testing. And now the first idea is to use the time that the textbooks usually spend in order to explain the intuition of software description languages, or taking time to read out the pragmatics of given examples. We use that time in order to tell the complete story. So we also reduce the formalisms to proper relevant sublanguages, but we use that time that's otherwise spent on intuition in order to tell the whole story. And there are two new items. So we use one as simple as possible but not trivial formalism to introduce the concepts of formal methods in software engineering that apply to all the others then in the course of the lectures. And while we are discussing the usually incomplete testing of code anyway, we complete the whole discussion by also having a block on program verification. Still, time is tight, so how do we now teach this material without overstraining our students? And here we propose a particular progression. So the line here is supposed to represent a staircase of levels towards a good overview over formal methods in software engineering. So we start in the topic area process management and use well-known process modeling languages on a semi-formal level. So here we focus on the proper definition of a concrete syntax with only an intuitive meaning. So we have roles and activities and artifacts and all that. From there on, we have our block on the principles of formal methods. So we use one simple formalism, in our case decision tables, that look like the one here on top. And we explain what is formal semantics, how does formalization look like, how can validation go, what are formal analysis, for example, for completeness here, and how do we interpret the results. This table here is supposed to illustrate the 4 possible outcomes that we may have from an analysis of a formal requirement with respect to the real requirement on the side of the client, which can be a true or false, positive or negative. Then we continue with the most complex formalism in our course, which is a formal variant of the well-known sequence diagrams. And here we have already a quite long distance between the concrete syntax, the diagram, the graphics here, and the semantically relevant information, the abstract syntax. And we also have a somewhat more involved automata-based formal semantics. Now, this allows us to go to the next level and turn attention to software modeling in general and focus on structural and behavioral modeling of software. So class diagrams, for example, have a less complex syntax than sequence diagrams, and the same for our sub-language of state machines. With the class diagrams, we practice once again the step from concrete to abstract syntax. With this variant of state machines, the students are already used to this dichotomy between concrete syntax, the diagram, and abstract syntax, the semantically relevant information. So here we can focus on complex software modeling, the pragmatics. Well, and finally, we take another step to deductive program verification. Here, the syntax is again pretty simple, a simple while language. The complex concept to understand here is that we are able to write deductive proofs for the correctness of programs. Okay, and that was already what I was able to put into the little video here. We motivated the need for formal methods in software engineering. We presented a complementation approach and this particular didactics of progression. There's much more in the paper, the details on the motivation and related work, the definition of learning objectives that we propose, details of the progression approach, and we report experience and data from 5 seasons of teaching, 1 implementation of this course design. And the data we have does not give any indications of student overstrain, neither with respect to time nor with respect to level or difficulty. Okay, that's all I have for this little video. Thank you for watching. Thanks